Okay, so now let's see on how we actually set this thing up for drawing. So now we have a new class here that we created that represents our OpenGL widget. So as you can see here, it actually inherits from QOpenGL widget, which is the one that we had in the user interface designer. So here it's actually kind of nice. Here you'll see a case of protected inheritance, which basically is a way to mix in capabilities. So the QOpenGL function is a collection class that has the classic OpenGL functions available for us, and we'll just bring them into the current namespace by using protected inheritance. So the whole thing here demonstrates the use of multiple inheritance in C++. Okay, so we have a GL widget constructor that allows us to set everything up, and then we have two overridden pure virtual functions, one to initialize the GL system and the other one to actually do the drawing, which happens in PaintGL. So these are the two. And the whole widget actually then encapsulates our shader program. We have the vertex array object that now allows us to specify the layout of the vertex array in terms of the interleaving of the vertex coordinate and normal data. And we have then, of course, two OpenGL buffer objects, one for the vertex and one for the mesh. And then, of course, our model, the teapot. So then let's look at the actual code. So again, the straightforward initialization here is right now that program and vertex array objects are initialized to the null pointer at this point, and the mesh buffer object or OpenGL buffer object is being set up as an index buffer so that OpenGL knows when we request an index draw where to get the indices from. So that's pretty straightforward. And then the initialize GL function is where we set up everything. So we initialize the OpenGL functions right here so that OpenGL is good and ready to go. We create our shader data. So we first read in the vertex shader, and this now is something that will, if you've worked with the OpenGL supervital code a bit, will be a godsend because Qt now when we compile the OpenGL shader allows us to actually retrieve error messages from the compilation, which happens right there. So if anything goes wrong in the compilation, the program is being terminated via a runtime error. But before that, we'll actually have a message that includes the error from the GLSL compiler. And so we now actually have access to the error messages there. Same thing goes for the fragment shader, of course. Then we compile and link the program. And so now the program is ready for binding to set up the buffers. We create a vertex array object to specify the layout of the data. We request static drawing because to allow for optimizations, because the model is not going to change over the lifetime of the program. Then we create the vertex buffer object for our vertices, bind that, and then we allocate the actual data. So that's what's happening here. So we're allocating enough data to hold the vertex normal and the vertex coordinate and normal data. And then we're basically saying, okay, here's a vertex array object, and saying, okay, well, the first location here will be location 0, and it's going to be 3 floats for the it's going to be 3 floats for the vertex, and then another 3 at the location number 1, another 3 for the normals, and so that's how you set these up. And then we just basically enable these. So, and these indices here 0 and 1 will actually get see back in the vertex shader, where we specify the locations for those 2 arrays by saying this is location 0 for the vertices and this is location 1 for the normals. So keep that in mind when we look at the vertex shader next. So we do the same thing for the indices. So the mesh indices don't change over the lifetime of the program either. So we just do a static draw. We don't, since there's no interleaving or anything like that, we don't have to set up a vertex array object. So there is no mixed or interleaved data in there. So, and all we have to do is just allocate and make the connection to the actual array for the mesh. And that's it, our program is set up and ready to run. So now when it comes to the drawing, here's where the draw happens. So we bind the vertex array object, bind the program, the vertices, and the mesh to the current context. The idea behind the binding really is we can of course now have several programs representing several objects and several types of draw procedures, so we can switch those out by unbinding from the current context and binding another program. So that's why we always have to do this. So we bind everything into the current context so that it ends up in our frame buffer. We clear the background to black. We enable of course, the depth test and color. And then we enable surface culling already at this point. Since we're going to draw just lines here, really don't have to at this point. But we can still go ahead and do that. And then we have the drawing now. This is index drawing, so GL draw elements instead of GL draw arrays. So with GL draw elements, we're drawing the lines. We give it how many lines do we draw? Well, we draw as many lines as we have entries in our mesh. And so the mesh's index type is unsigned ints. And that's that, and that goes because we've set it up in the vertex array object and in the vertex buffer objects. So OpenGL now knows when it sees this to actually go and to actually draws the array by retrieving the indices, retrieving then the vertices from the array via the indices, and then hand it off to the shader. And so, and that's this. So let's look at the shader, vertex shader here. Very, very simple right now because we don't do any lighting or anything here whatsoever. So we're just basically specifying, okay, well, the shader has 2 inputs, the vertices and the normals. And here the location 0 and 1 correspond to the location 0 and 1 where we actually set everything up in the vertex array object. And then all we do really is a pass-through shader where we just output the position in the for the vertex, and we're just basically making sure that, of course, since OpenGL expects everything in homogeneous coordinates, so we need to add the fourth homogeneous component and set it to 1 at this point because we don't do any perspective or anything like that. So we take in our 3D vertex data, create a 4D vertex out of that, and hand it off to the next shader stage. And that's what's happening there. Very, very simple. Fragment shader, also very simple because this is a simple shader that just creates our color. And so we're opt for a nice candy apple red here. So this is RGB alpha. And so we just say, okay, draw everything in red. And that's it. So, that's basically all we have. So the main window really hasn't changed at all. And so all we have to do now is to go ahead and execute that, compile that, and run that. And we should see our teapot on the screen. We haven't done anything to the default locations, default clip space. Everything is standard OpenGL at this point. And when we compile this, then we'll see that indeed now we're getting this. Remember that we are at location 0, 0, 1, looking down the negative z-axis. That's the default viewpoint right now. So we're looking at the bottom of the teapot. Because the aspect ratio is not 1 to 1, right now you see that the teapot is distorted. Clearly we're looking also into the bottom of the teapot right now. But other than that, well, it's recognizable as a teapot. So now we have to fix everything so that we get this in the center of the screen. And we undo, of course, the distortion from the viewport and all these things, and eventually connect the sliders to manipulate it, and then, of course, add the normals to it and then the lighting so that we can actually start drawing triangles. We can actually switch, and let's do this right now, just so that you see the effect of doing that. We can switch the drawing to triangles. And because of the absence of lighting, there's really then all it's going to be a red mess. So let's do triangles, and we compile this. You see, of course, that all the triangles are being filled. The one thing, however, that you do already see is backface culling, so which is just based on winding order only. So we're now actually seeing only half of the triangles. That's another nice thing we can do. So let's go back and actually disable backface culling, and then we'll see a little bit more of this here. And so we'll see now all the elements. And so that's some of the things we can play around with. And let's just go back to the original with the lines and recompile this. And this is then the model again in wireframe.